Our world is incredibly big, with really heavy objects and complex forces. But everything can be broken down into incredibly small pieces called atoms and molecules, and even smaller pieces called protons, electrons, and neutrons. Even though we can't see some of these particles, they still have masses. But how do we measure them? Well, let's try using a scale. We can measure objects with great precision using very accurate scales. But what happens when we can't make scales any smaller? Our measurements will become less accurate the smaller the object. Take carbon for example. Lots of things are made out of carbon, like you and me. We can be measured. However, individual carbon atoms are too small, they can't be seen, let alone accurately measured. You could take a chunk of carbon and weigh it to find the mass of one carbon atom. But then we come across a problem. There are many different carbon isotopes, each with different masses. If only there was a way to separate each particle. Luckily, we have a technology called mass spectrometry that can accurately measure the chemical makeup, the mass-to-charge ratio, and even the mass of a sample and its components. Mass spectrometry is a field of science that uses technology with a fairly simple concept. An accelerated mass spectrometer is a measuring device that is incredibly precise. First, the sample is passed through a beam of heat to vaporize a substance, changing it into a gaseous state. This makes the substance easier to work with. Second comes ionization, which consists of giving an element or the molecule a positive charge. Since you can't give protons, we remove the electrons instead by shooting electrons at the sample molecules. As soon as they become positively charged, the positively charged compound repels the highly positive core of the electrostatic accelerator, and all the projectiles shoot out of the small opening. They continue in a straight line and are deflected by the electromagnet. After deflection, the particles hit a sensor. Depending on where each particle hits the sensor, which is a silicon barrier, it is given a mass-to-charge ratio that can be then used to determine each particle's mass. If you were measuring the deflection of carbon, for example, you would first enter with the knowledge that carbon consists of many isotopes, but mainly carbon-12 and 14. Since they have the same charges, but carbon-14 has more mass, you would notice that carbon-14 with the more mass is less deflected than carbon-12. Mass spectrometry is used to help date fossils and other items. Carbon-12 and carbon-14 isotopes are measured to determine the age of a sample. This method of dating is called carbon dating. Radiation from the sun causes carbon-14 atoms to form in the atmosphere, which is then transferred to all living things. When an organism dies, no more carbon enters it. The carbon-14 decays, while the carbon-12 stays near its constant. By comparing the carbon-14 to carbon-12 ratio in living organisms to the carbon-14 to carbon-12 ratio in dead organisms, it is possible to determine the age of the dead organism using the half-life of carbon-14, which is 5,700 years. In geology, mass spectrometry is used to find oil deposits by measuring the amount of petroleum within rocks. While in forensic science, mass spectrometry is used to analyze a crime scene. For example, blood can be analyzed to determine the use of poison. Biologists use mass spectrometry to measure proteins. Pharmacists can use mass spectrometry to determine the drug levels within body fluids. An accelerated mass spectrometer uses a very small sample size, reducing the damage done to the object. For example, if you take a sample from a precious painting, you want to take the least amount of material for carbon dating so you don't destroy the masterpiece. Mass spectrometry can provide lots of different information, and the data gathering process is efficient, quick, and accurate. Scientists can use the information acquired to give the compound a mass per charge ratio and the time the object has existed for. Mass spectrometry has its cons. Like all scientific experiments dealing with small atomic particles, the operation is expensive. Industry-level mass spectrometers cost $100,000 to $800,000, and they are incredibly specialized mass spectrometers that can cost over $1 million. Furthermore, to operate the machine, you need to be certified. And if you don't own the measuring device, or you're not certified, you'll need to send your sample to the lab to get it tested. This process of sending the sample to the lab is costly and it takes a long time to acquire the results. Alternatives to this technology are a necessity because mass spectrometry is fairly expensive. One alternative is infrared spectroscopy, which is much cheaper but can only be used to identify chemicals present in a sample by observing it under infrared light. On the other hand, mass spectrometry can determine the weight and structural features of a compound. This method, however, cannot determine the mass of the particles. Another alternative is gas chromatography, which is also just like the cheap previous alternative, but again cannot find the mass of the compound. It is still a good alternative because unlike mass spectroscopy, it only costs a value of half a car. Produced by Josh, Gurkaran,